So welcome to the third debate of the RSS workshop on Sim2Real for robotics. The theme of this debate is, for successful Sim2Real transfer, there is no alternative to accurate simulation. We are Juan and Melissa from the Robotics Lab at McGill University, and we will be the moderators for this debate. Note that there is a pre-poll on the RSS virtual conference website where you can submit your opinion on this proposition before the debate, and there will be another poll after the debate so that we can see how public opinions may have shifted by the arguments of our invited speakers. Before introducing our speakers, let us explain the motivation for this debate topic. The debate starts with the assumption that we agree that simulators are useful sources of data for robot learning algorithms. In this sense, Sim2Real describes a situation where some aspects of the world are simulated to prepare our robots to learn in the real world. The question we aim to address in this debate is, how should we do Sim2Real? Techniques like domain randomization show us that we can train our systems on fairly inaccurate simulators by focusing on generalization performance. On the other hand, improving the simulator accuracy simplifies the learning and control algorithms for successful Sim2Real transfer, as is commonplace in engineering with analytical modeling and system identification. We are very excited to hear the opinions of four experts in robotics on whether the reality gap, the difference in simulation and reality, would be easier to close by improving simulation accuracy or by developing algorithms that extract useful information from crude models.
This debate will be structured as follows. We will start by introducing our four panelists, two arguing for and two against the proposition. Note that we are asking our speakers to take a particular opinion in the debate, which may or may not reflect their personal opinion. Each speaker will have 5 minutes to deliver their opening statement. We will then transition to the actual discussion and wrap up the debate approximately 5 to 10 minutes before the end. Juan and I, as the moderators, will try to stay out of the debate, but might interrupt in order to make sure we cover as many interesting questions as we can. I am now going to introduce the speakers. Arguing for the proposition on the pro side, we have Dieter Fox. Dieter is a professor at the CS department at the University of Washington and the director of the Robotics Research Lab at Nvidia. He is widely known in the robotics community as one of the co-authors of the probabilistic robotics book. He has published more than 200 technical papers, and his contributions include work on applications of machine learning techniques for SLAM, robot control, and robot manipulation. His group has also worked on vision-based modeling of physics and leveraging simulation platforms for data-efficient learning. The second proponent is Karen Liu. Karen is an associate professor at the CS department at Stanford University, where she leads the movement lab. Karen's work has demonstrated how complex and realistic human motion can emerge from optimization on physics-based simulation, with contributions on numerical simulation, optimal control, and application to character animation, assistive robotics, robot locomotion, and robot manipulation. It's a great honor to have you both on this debate. Thanks a lot for joining us.
Thank you.
Fun to be here.
On the opposing side, we have another two outstanding researchers who will be arguing against the proposition that accuracy in simulation might not be essential for Sim2Real. First, we have Anca Dragan. Anca is an assistant professor at UC Berkeley and a research scientist at Waymo. She's also one of the founders of the Berkeley AI Research Group. Anca's research focuses on algorithms for cognitive modeling of people and their integration to robot control and planning. Her contributions include formalizing human intent with mathematical models for behaviors like legibility or courtesy, and work on motion planning, optimal control, and inverse reinforcement learning, with applications to assistive robotics, quadrotor navigation, and self-driving cars. Thank you for joining us, Anca.
My pleasure. Thanks for having me.
The second opponent is Shuran Song. Shuran is an assistant professor at the CS department at Columbia University, where she leads a lab working on computer vision and robotics manipulation. She has an amazing track record with some of her work, including the Sun RGBD and ShapeNet benchmark datasets for 3D vision. Her extensive work on robotic manipulation includes learning affordances for grasping, learning physical properties from object interactions, and learning how to throw objects with simple physics models. We're really excited to have you here. Thank you for joining us, Shuran.
Thank you.
Okay, so now we are ready to hear the opening statements on the theme, for successful Sim2Real transfer, there is no alternative to accurate simulation. We will alternate between the for and against side. So the order will be Dieter, then Anca, then Karen, then finally Shuran. So Dieter.
All right. Yeah. Thanks a lot for having me and giving me the opportunity to argue for the right side of this debate. So first of all, of course, I guess, as you already said, we all agree that we do need simulators, right? Because that's kind of the cheapest, safest, and fastest way to train our robots. I think overall, of course, the best we could aim for is if we had simulators that can really one-to-one map the real world, because then we could train our robots in these simulators and they would immediately work in the real world. So that is kind of the optimum we can really achieve. So what do we want from our simulators? At the high level, we want them to model, to provide the right input-output behaviors for the world a robot operates in. So that means, for example, that if the robot performs action, sends control commands, that the world reacts in the right way with respect to the physics, the interaction of objects, the motion itself. We want the simulation to provide also sensor information that the robot would see in the real world. That means touch feedback, that includes photorealistic rendering of images that the robot might see. And we would like to actually have the robot interact with people that behave at the same way they would behave in the real world. And these kind of simulation models, they should include, of course, physics reasoning, but all of this is happening at different levels of abstraction. So when we talk about accurate simulation, it's really the question, what do we mean by accurate, right? Because even all these so-called accurate simulators that we know, like physics, Bullet, Flex, Muchoco, Dart, they are all already a wild abstraction of the real physical world. So we need to reason about simulators being accurate with respect to the input-output behavior that we want them to provide at the right level of abstraction. So on the one hand of the debate here, we have people who would argue that these simulators need to be accurate with respect to that behavior that we want to see in the real world. And on the other side, we have people who think that we can just get away with having some hand-wavy approximate input-output model that we can then use to train our robots. And for simplicity, I'll just call this the sloppy simulation side of the debate here. It makes it easier to kind of put things apart. So I believe that only if we have really accurate simulation, then we can really train robots in these simulators so that they actually function and operate as we desire in the real world. If you have sloppy simulators, this might work in certain circumstances, but in many situations, sloppy simulation could really generate behavior that is totally unpredictable in the real world because you've never tested it in these situations. So again, we might do some adjustments in the real world, but if you have a bad simulator, you might spend more time retraining your policies in the real world just because you have to undo all the bad things that your robot trained in the bad simulation. And this is clearly not doable if we want to have robots that are in safety relevant applications in industrial settings where you don't want to hurt people, for example. I think another key advantage of having accurate simulations is their generalization capabilities. So they're built typically based on physics model, physical understanding of the world, and therefore they can simulate a broad set of environments and domains, and they can generalize to these. If you have a bad simulator that might work in setting A, if you now want to apply that to train a robot in a setting B, you have no idea how that simulator is going to behave, and hence what your robot is really going to learn in that new setting. So if you have inaccurate simulation, every time you want to move to a new domain, you have to really fine tune and tweak your simulator from scratch again, because you don't know what's really going to happen. There are now these domains like that might help with this. One aspect, of course, that's relevant is domain randomization, where the idea is you randomize over the simulation settings and thereby make the trained policies more robust to the discrepancy between sim and the real world. I think this has worked reasonably well in certain settings so far, but I think if we go to more complex settings, domain randomization is not going to work as well with bad simulators, because if you have an inaccurate simulator, you have to randomize over many, many more variables that you don't even understand how they relate and how they work. And therefore you make it so much harder for your robot to train in these settings. And also the same is if we want to use real world data to fine tune our policies, I think a much better way to reuse real data is to fine tune our simulators, because that way our simulators can serve as kind of data multipliers. If you get real world data, you further refine your simulator, and then you can generate even more data. So to summarize, I think there's just no way we can ever be able to train robots to do a complex task in the real world based on inaccurate simulators. The only way is to have accurate simulations and thereby keep the gap between sim to real manageable. Thank you.
For your statement. So now we can hear the statement by Anca.
All right, here it goes. So let's see, I'm gonna start with the boring, obvious things first. The boring, obvious things being, I'm really gonna pick on this accurate part, right? So domain randomization was mentioned before, and you know, that basically to me means that you don't need to know the exact parameters. You don't need to know the exact coefficient of friction. You don't have to put that in your simulator. You can just tell the robot that it doesn't know about that, and it will figure out how to deal with it and transfer it to the real world by starting to learn about that coefficient of friction. So I think that's a powerful tool to get around inaccuracies. Listening to Dieter, one thing that came to mind was this implicit I think implication he made that you're going to have a buggy simulator and kind of overfit to that, and you're going to have to undo that in the real world. But I think, again, diversity is an alternative. Diversity is something where you say, if there's stuff that we can't actually model accurately, then we're going to not pretend like there's one true parameter and that's fixed and that's how the simulator is going to work. Instead, we're going to rely on variations of that so that the robot can actually understand about that uncertainty. So from that perspective, I want to point out that if we take the approach of accurate simulator, there's going to be one true simulator and it's going to be high fidelity, actually accurately representing the world, we might even run the risk of lulling ourselves into this false sense of security. Like, we have the simulator, it's accurate, we're going to go. And then, you know, guess what? Simulators are never going to be completely accurate so that you do magical transfer and everything just works out in the real world. That's just not going to happen. There's always going to you're always going to have to develop techniques that understand that the simulator is inaccurate and actually are able to do adaptation in the real world. So really all that we're talking about is what is a good way to initialize, what is a good way to develop some sort of prior for the real learning that's going to happen in the world, the adaptation that's going to happen in the world. So that's kind of, those are maybe the sort of more obvious arguments. I was thinking of an argument that's maybe a little bit more subtle or more nuanced that I think kind of goes along this statement that all models are wrong, but some models are useful. And so I think accuracy is not actually the be all end all. It's okay to have a wrong model so long as it's a useful model. So it's okay to have a wrong simulator if it's a useful simulator. And the way I think about it is, I think of the robot, the policy, as computing a best response to the model, to the simulator, right? You give it a model and it produces the policy that is optimal under that model. And so even if you want the robot to perform perfectly in the real world, you don't actually care about the accuracy of that model, right? You care about the performance of that best response. And the thing is, there are gonna be many models that induce the same exact best response. So accuracy is kind of a red herring, because really what you need is whatever you need to tell the robot, such that when it computes that best response, when it computes its policy, it ends up with the right policy. And so I think that's kind of a really, once you realize that there are these multiple policies that are just as good, you don't have to get all the details right. You just have to get the details that matter right. And I think that's kind of the difference that I wanted to hone in between accuracy for accuracy's sake versus whatever needs to be useful. There are two more points that I'd like to make. One is that I actually object to the idea that, simulators are a must. I might object to simulators in general. And here's what I mean by that. I like models. Models are a must, I think. But a model and a simulator are not one and the same. Because when you're trying to build a model, you're actually interacting with the world, gathering data, the data that is going to be useful to you, and developing the model involving your policy. when you're building a simulator, we're sort of making this assumption that there's data that's collected somehow, right? We don't control that, we don't have access. So it's like a black box. Data comes to us, we build a simulator based on that data. And then we train the robot, maybe with model 3RL, to work in that simulator, right? And that distinction doesn't make sense to me, because I think there has to be this interaction between the way you collect the data, right? And the way you're actually training the policy for that data. So you kind of have to have the closed loop between what you actually need to know about and gather data there. And I think, so that's why I think that the notion of a simulator might not quite be the exact notion that we mean to have here. And then finally, I'll say that you know, I deal with humans. That's what I like doing. And so a great example of, you know, accuracy being kind of a red herring is, I think, interaction with humans. Because I think we all agree that we can get robots to coordinate and collaborate with people without accurately simulating the human brain. I have to believe that, because I'm not going to accurately simulate the human brain, right, in order to actually get these robots to properly interact. And so, and I think a lot of people believe in that. I don't think a lot of people believe that you know, there has to be a way to get good behavior out of the robot without getting all of the details of what's happening in my brain properly, so the robot can interact with me. And I agree to a certain extent with Dieter's you know, point about, look, there's levels of abstraction. You have to get it at the right level of abstraction. And so I think that kind of goes hand in hand with, you know, what's the, you want to do that in whatever way is actually going to be useful for that best response. That's what you need to get right. And so you can try to go for a level of abstraction that's useful without modeling the underlying thing. What you're saying at that level of abstraction is still going to be wrong, right? This happens in hierarchical motion planning all the time. You can't just plan at the abstract level. You have to go into the details. But at the same time, there has to be a balance where you really want to focus that accuracy towards what actually ends up going to be useful, and be aware of the uncertainty over the things that you can't actually model accurately. And I think that uncertainty is really key. And by lying to ourselves that we're building a great simulator, we might forget about that uncertainty, and we might forget about the fact that we're going to need transfer in the real world. Okay, I'm done. Thank you.
For your opening statement, so we're now ready to hear Karen's opening statement.
All right. So I think I have a few. I have some response to Anca's. Anca makes some good points, but I have some counter arguments. Should we wait it until we have this cross conversation, or I should do that during my opening?
I think it's okay if you like. You should.
Okay. I'll start with
Karen, bring it on. Let's see what you've got.
We'll start with the opening. So the way I interpret this debate statement is the following: given an important or imperfect set of simulation tools we have today, we as a community should invest more on improving the simulation tools instead of investing on control methods that work around flawed simulators. Okay, so that's how I see this the debate statement. So first, I need to define what I expect the simulators can eventually achieve. Okay, not today, but in the near future. I will argue why this is a good simulator worth pursuing, and I will further argue that once we have a simulator in place, the remaining issues related to Sim2Real becomes trivial or manageable. So to me, a reasonable, achievable simulator is one that predicts the next future state correctly to the extent of our collective knowledge about how things move in the world, and also to within the distribution of the data used for training various components of the simulators or for identifying the parameters. So in this debate, I will assume that the required simulation speed can be achieved by unlimited computation resources available today or in the future. So I don't want to talk about how slow simulator is today. I will also assume that the modeling of the world can be done by a combination of modularized modeling techniques and unlimited crowdsourcing. I know these are big assumptions, but I kind of want to focus my argument without being distracted by these things, things that could be achieved by a lot of engineering effort. This is not an easy feat, but it is theoretically achievable because we assume that the simulators will only be as good as what the data or our prior knowledge are. If our simulation techniques can achieve these, reach those full potential I described, then we will have a task agnostic extensible dynamic model, which can be can incorporate any new piece of knowledge in physics or data and improve the predictive capability monotonically. So what is an alternative if we don't have an accurate simulator, if we have a sloppy simulator? Well, we can develop control policy to compensate the inaccuracy of a dynamic model. And I argue that this is a less effective approach because the necessary treatment to overcome the inaccuracy simulator might be different from task to task. The policy for one specific task might learn to exploit the inaccuracy of a model in one way, and then the policy for a different task might learn another way. So coming up with all those workarounds for different control tasks is just impractical and tiresome. So we never know, basically we never know, what we are overcompensating in one area, inadvertently, compromise other area. So the effort we spend on improving the control benefits only the task at hand, but it does not accumulate. In contrast, any improvement in simulation, be it a new empirical contact model, a more accurate numerical integrator, or a better geometry processing technique, or even just one extra pair of training data, they will amass and asymptotically approach a perfect predictor for the next state. So when such a asymptotically perfect simulator, let me call it that way, is in place, then I think that the Sim2Real, it becomes a lot easier, right? So there's still remaining challenges. For example, even the parameters we usually consider constant, such as center of mass or inertial property, they might change over time. So we'll have to constantly update the calibrated simulator using data. And other things that Anca mentioned is that humans, right? If you have other agents in the simulator, in the environment, whose behavior or policy we cannot observe, then we will have to model that. Otherwise, it will undermine the accuracy of the simulators. But I really think that if you accept those caveats, like I described, then the developing an asymptotically perfect simulator is the most effective and rewarding way to evolve or to solve the Sim2Real problems in the long run. So that's my argument.
Much, Karen. And now finally, we'll hear the opening statement by Shuran.
Cool. Okay, so I will argue why I think that accurate simulating is not the only way for better Sim2Real transfer, and why sometimes using a simple and inaccurate simulator can actually be beneficial. So first, I think the fundamental challenge of an accurate simulator mostly comes from two aspects. One is formulating and computing the physics. The other is actually obtaining all the physical parameters of all the objects in the environment and also the sensors. So I think for the first challenge, we can easily or possibly improve with more compute power and with better physics formulation. But the second challenge is actually really the hard part to address. So just as an example, so accurately modeling a process like aerodynamics is an expensive but achievable process for a specific domain. For example, we have really high quality simulation for aircrafts that is really helpful. However, those simulation systems do not work for random household objects, since that we don't have the precise physical measurement of all those objects. And as Karen just mentioned, these properties may even change over time, which make it even more difficult. So at some point, I think we need to accept the fact that accurate simulator just that perfectly match the real world is just too expensive to achieve. But at the same time, I think there are also many alternative ways to improve Sim2Real transfer by better leveraging those inaccurate simulators. So first is that with a simple but fast simulator, we have an opportunity to really scale up the process and therefore focus on the diversity of the simulation environment instead of their accuracy, just like approaches like domain randomization that target on making the sim distribution large enough so that the real world becomes just a subset of that. And another direction I think worth to think about is to use better ways to combine this simple but inaccurate simulator with efficient real-world learning. And the key is actually to really, for the system to really understand which part is inaccurate from the simulation. So for example, the idea of residual physics is to use some physics models to provide initial estimates and then use learned residual terms to compensate for the object dynamics that is hard to measure or model. So back to the earlier example, we have described that modeling an arbitrary object's aerodynamics is extremely hard. However, if we simplify the problem by treating all the objects as a dot in a vacuum, then all of a sudden, their projectile trajectory is only influenced by their initial velocity and nothing else. So this dot in a vacuum model is clearly inaccurate, but it's good enough to provide a strong prior for the planning. So, and also since it's so simple, it can be easily integrated as part of the control algorithm during the test time. And then the algorithm can focus on learning the residual terms for different objects through real-world interaction. So the key here, again, is knowing which part is inaccurate and needs to be learned. So in contrast, if we have a more accurate but complex formulation, it might become too expensive to be applied in test time. And also, once we start to design simulators that's tailored for certain tasks or objects, it will also make the simulation system less generalizable in practice. So in some sense, a more accurate simulation may actually limiting the system's ability to adapt. So I think in conclusion, I believe that an accurate simulation is both costly and sometimes unnecessary. And I think instead of only focusing on the simulator's accuracy, we should really consider other methods that also make the simulation more diverse, simple, or generalizable. So that's my argument.
Right, thank you very much for the very interesting opening statements. So I guess one question, like we could hear some agreement in, for example, that there's a need to pick the correct level of abstraction for your simulator, but that also seems like a pretty hard problem in the first place. So relatively recently, a well-known researcher in machine learning stated on social media that the biggest misconception in DeepRL is that Sim2Real is hard, alluding to the successes in engineering where Sim2Real is addressed, at least at the dynamics and controls level, by mathematical model and system identification, followed by the design of controllers. This is in line with recent Sim2Real successes, like, for example, the Rubik's Cube work by OpenAI, where there was a lot of effort in the modeling to produce the successful domain randomization task. So now the question is, like, can Sim2Real be really just reduced to accurate modeling? And even so, accurate modeling is hard. Is it easier to just find like the correct level of abstraction? Is it going to be easier than just finding a better accurate model? Like, I guess to rephrase it, so it's are we limited to really simple abstracted models for Sim2Real success?
Are you asking for everybody or whoever something?
So, yeah, if anyone wants to go first, or I could also pick someone.
Yeah, I see. Okay, so I think it's actually quite related to what I just said. It's really important to know what are the parts that can be accurately modeled and what are the parts that's hard to model. I think I kind of summarize it as like the physics, like control, we actually know very well how to model that. But estimating the physical properties about the object, that's probably the hard part. So I think finding the right abstraction level is probably highly related on we know which part we can accurately model and which part is hard.
I'll add to that, I didn't get a chance to mention in my opening statement about the abstraction level. Because I do agree to some extent, but I think there's this big caveat that's pretty important. And the caveat is that accuracy at the abstraction level doesn't seem to be the right thing to go for. So I think if you pick an abstraction layer that's not, the lowest level, then inevitably you're not going to get perfect accuracy at that abstraction level because you're not capturing the underlying things that lead to those higher level decisions or higher level actions or properties. So you're not going to get accuracy perfectly at that abstraction level. So no matter how you slice it, you're not going to get perfect accuracy. And then the question really becomes, where do you put the accuracy in versus what is okay to not have accurate. So for example, I have robots going around, the quadrotors going around people. And that's what I was trying to say with the best response thing, that I can write a model of the person that's very clearly, that's first at a level of abstraction that's actually important to the robot, but second, that's very clearly inaccurate even at that level of abstraction. And yet, right, the important bit is when I run planning for the robot side to deal with that human, what is that plan going to look like? Where's that policy going to look like? And I can very easily lie to the robot about how the person is going to behave, so long as it induces the correct response from the robot. So long as the response would be basically the same or very close to the same as the response it would have to the accurate model that I can't get anyway because I don't know what people do in their head.
I can chime in again also on this notion because you brought it up with the OpenAI and the domain randomization for the manipulation tasks. I think if the less accurate your simulator is, right, the more domain randomization you have to do because you just don't know what to randomize over, right? So that is why we see a lot of work where, for example, in the image domain, suddenly you're generating images where objects have totally wrong colors, the lighting conditions are totally crazy, and you do that also on the physics side. So I do agree that we need domain randomization, but if we have good physics simulators, then at least we know what to randomize over, which means we know that we have to randomize over masses and friction parameters. But again, with bad simulators, you do not have that knowledge, and suddenly you're randomizing over way too many things, and it's way too hard to learn a policy that actually applies then later on. I think that's a big problem with inaccurate simulators. Also to Anca's point, of course, with the level of simulation with humans, I agree that there's no way we're going to simulate human behavior starting at the neural level of the human brain. And that is where the abstraction level comes in clearly, right? But I think at that level of abstraction where I want to generate behavior of a human so that I can train a robot to interact with a human in a natural way, I think at that behavior level, we do need to be accurate because otherwise our robots might just totally misinterpret what a human wants to do in the real world, right? If it's trained in the wrong way.
So I sort of agree, but I think I'm pointing out that we're never going to be accurate, even at that layer of abstraction, because we don't know what's happening in the brain. And so we just can't. We just can't have a model that's perfectly reliable at an abstraction level that's not, the human brain. And so there are going to be errors no matter what you do. And I think that's in a sense the key message that I'm trying to convey here is that you want to make sure that you have the right amount of uncertainty as opposed to committing to a model saying, okay, this is the thing, it's the most accurate I'm going to get, let's go with it. But you actually are able to capture what you don't know and give the robot the chance to go ahead and learn about it or, be risk averse with respect to it or whatever you want to do. I think that's the part that's important. And then the other thing that we found, Dieter, that's really crazy is that given that you don't have perfect accuracy, because I agree with you, if I had perfect accuracy at the right abstraction level, right, everything's great. But we're not going to have that. And now if I accept the fact that I'm not going to get to perfect accuracy, we've found that you can improve with humans in particular, but I think it holds of physical environments too, that you can improve the accuracy of the human model and make the planning for the robot worse. So improving accuracy doesn't perfectly correlate with the robot performance, right? Because you're running it through a planning loop or through an inference loop. And so if I had perfect accuracy, that would result in a perfect response. I agree with you. But now I'm epsilon away, and within that epsilon, I can squeeze in more accuracy and actually hurt the robot's performance. That's the paradox. And I can prove this to you. It's just, it boils down to like Bayes' rule and stuff like that. It's a very simple thing, but it's very counterintuitive. I think you can make perception better and then the planning gets worse. Accuracy does not actually one-to-one correlate with robot performance.
Let's take Karen first. Go ahead, Karen.
Oh, okay. Thanks. So I already accumulated a lot of arguments here, so I don't know which one I should address first. But let's just go back to what Dieter said about domain randomization. It becomes very ineffective if you you have a really sloppy simulator. And I think that's definitely true. And especially when you do domain randomization, you know, even though you know which parameter to do it, you also need to know, roughly know the range to do it. You know, like when things becomes, when you're dealing with, you know, bipeds or something that's more task critical task, or you know, like it's a more critical task, like the feasibility region is really small. Domain randomization is just not, or naive domain randomization is just not a good way to go. And also I want to go touch back to Anca's opening statement a little bit. I totally agree that, you know, you don't need to model every possible details. You just need to, you know, model or simulate the important details. But the problem is you don't know what details are important at the beginning. So what you would end up doing is you build some policy, you develop some controllers, and you try it and fails, and you go back to figure out what, you know, okay, maybe I'm not, you know, randomize the right parameters. So, and then the problem is that you do that for this one particular task and then move on to the next task, you're going to do that again, right? So I agree, you know, only a small handful of, you know, parameters might be important for your task, but you don't know in advance. It's very difficult to do that. And then the final thing I want to touch on is the abstraction versus, you know, accuracy. I kind of definitely agree that, you know, for pretty much any problem we're solving, especially humans, you need some level of abstraction. But I do think that, you know, even the abstraction level or abstract representation, you still need accuracy, like what Dieter said, the behavior level. And to me, a lot of things that Anca mentioned is a control issue, right? Like we don't know how brain works, but brain is the controlling part of it, right? The simulation that, at least the notation that, or the interpretation of simulation I have in mind is more of basically the governing rules, like given a state, given an action, what's the next state? And that action, I think the problem that we can't do very well with humans, we don't know what action that humans, you know, neural system produces. But if we do know that, and then we can really just reduce the level of abstraction at the joint torque level, then it becomes a physics problem, and we know how to do it well. Well, we don't know very well, but there is a path toward that, right? If we have a better biomechanics, you know, more investment on that, then we could have a good simulator for human on the physics part. And a lot of the issue behavior, that is a control part. And I want to, you know, separate that from when we talk about simulation.
But you can't, right? Because the dynamics, the moment you put the robot in a world with people, the dynamics of the world is governed by.
Yeah, I fully understand this argument about humans specific is tricky, right? Because we are, you know, we're gonna sort of mix simulation and control. And to me, there is a very a clear mathematical distinction between simulation and control in most of the mechanical systems. Human is such a, you know, special case that I don't know how much we want to just, you know, devote our debate on that. We could, but you know that.
And just on the topic of humans, actually, I'm starting to think about we as humans, we're actually always using an imperfect predictive model. That's when we are acting around. Like we don't have a perfect predictive model on physics. We don't have perfect predictive model on other humans' behavior. But we can function really well because we know that it's imperfect, and we actually try to model the uncertainty on top of that. And for a lot of times, we don't try to improve our accuracy on predictive model, but actually how to focus on like reduce the risk or the uncertainty around it. So.
Okay, I want to respond to that also. I think Shuran and Anca are confusing or mixing two things that I think don't actually or shouldn't be mixed. And that is, Anca also said that, for example, we don't care for our robots if they have accurate internal models, right? All we care about is that they execute the policy that operates the right way in the world. And I totally agree on that. And I totally agree also that these models that the robot is using to make these decisions don't have to be accurate or anything like that. But this is confusing the point between the policy that we try to teach our robots and the environments in which we try to teach them. And that is what this discussion is about, which means the simulator should still have a very good model, an accurate model of the world, such that these policies that we then train, they don't have to be accurate, but they need to be trained in an accurate replication of the world. And I think that is a very, very important distinction between the environments in which we train the robots and the models that these robots are learning to use, which can be totally different. And that also relates then if we, because Shuran brought up this notion that we humans have, our internal models are also, let's say, sloppy. And I totally agree on that. But imagine you would have a little baby and our babies were trained in a domain randomized world, right? With colors changing constantly all the time. The physics of the world change all the time. Nothing is predictable. I think our babies would be totally confused and might not be able to learn anything. So why do we make our robots learn things that are much harder than actually the real world is? So we should come up with domain randomization techniques that actually are realistic domain randomization rather than this crazy wild domain randomization that we're using a lot.
Exactly. Actually,
my dog agrees.
Exactly. I think the domain randomization that you mentioned before is probably like the entry-level domain randomization. But that actually highlights the point that instead of just thinking about accuracy, we should think about how to use alternative methods like better domain randomization to improve the algorithm, right? And I think the babies actually, we didn't train it on a domain randomized system, but we do train it with a lot of imperfect simulation, like books, like movies, and it works well. Like they learn generalizable knowledge from those imperfect simulations. Yeah.
So I kind of want to push back a bit on that. So I think we train our babies on a perfect simulator. It's just their sensing is not perfect, right? It's a perfect world, but you don't sense perfectly. So I think the key here is that we need to have a good simulation for the world and a good simulation, a perfectly imperfect simulation for the sensors.
I want to
or a accurate simulation to simulate imperfect sensing. I guess that's what I mean.
Yeah. Dieter, just to clarify, I very explicitly do not mix the policy with the environment. I'm making the argument that the accurate environment, the 100% accurate environment will lead to the policy you want, but there will be a lot of other environments which lead to the exact same policy, assuming the optimization process that, operates an environment and computes the policy. And then I'm making the additional point that when you can't have the 100% accurate environment, making the environment more accurate is not perfectly correlated with making the policy perform better. That's what I meant.
Oh no, I totally agree on that point, but I think, and that is exactly what Karen just said. By accurate simulation, we do not mean fully deterministic simulation, right? Accurate simulation means just that it models the behavior, the input-output behavior of the world well, which includes noise in the sensor data and noise in the controls. But by having accurate models behind that, we know how that noise affects these kind of relationships.
Yeah, and I guess I'm saying I agree with that 100%, and I'm saying that even if you have a stochastic, there's a thing that actually models the uncertainty properly. You can measure accuracy on that, from the perspective of you can reduce your uncertainty more and make it more aligned with the real world or something like that. And you think that increases the accuracy. If you actually measure the probability of the thing, right, of the ground truth, it's higher. That's what I mean by accuracy. So you can improve that metric and make your policy worse, because your policy is then a response to the environment. So there's this additional loop that goes in. And that's the really counterintuitive crazy point. But we shouldn't assume that by pushing on that, even that probabilistic notion of accuracy, we're making automatically the robot's policy, which is the optimal response to that environment, better.
But I suspect that is because we may be using the data then in the wrong way, right? Because in the limit, if we had, which we all agree on, absolutely truly perfect simulation, there would be no difference between the real world and that. And if that simulation wouldn't result in the best behavior, then somehow how you're learning the policies might be.
Yeah, the 100% accuracy results in the best behavior, but then you know, the difference between 92 and 98% doesn't necessarily translate in an improvement in the policy. It might, in fact, in some cases, make the policy even worse. I think there's a correlation, but it's not a perfect correlation.
Okay.
Does anyone else have anything to say on any response? Because we're already at the 15-minute mark. So I guess in the interest of time, we should go through the closing statements based on what the arguments that we've heard. And it was nice to hear like there was some agreement, but also some disagreement on this topic. So let's start the closing statement with Anca, maybe.
Okay, I didn't prepare a closing statement, but I guess I'll summarize everything with, I think there's agreement, there's quite a bit of agreement, right? We all agree on, we need some abstraction level. We agree on the fact that it's useful to model the world and we shouldn't just, you know, throw in random things and randomize them and hope for the best, because that's gonna make a robot that has to deal with all of that uncertainty really render it ineffective. I think we all agree on how important the uncertainty is, or the, you know, to model what you don't know or you can't know, so that the robot can learn to actually go ahead and figure that out in the world, or be risk averse or whatever. So I think those are points of agreement. I don't know what we disagree on. I think I think that maybe we're saying that maybe the point of contention is that there's a way, I would argue that you can try to go for accuracy, and that for the most part, improving that accuracy will result in better policies, but that in some cases it won't. And it's complicated. I agree with Karen that we don't know what's important and what's not important to get right, but to a certain extent, that's why I think that we do need a loop between the model or the simulator and the world, so that the robot can actually go in and collect the data that it needs to collect and model those aspects of the world better. And we need to automate that rather than, you know, Karen made it seem like it's going to be some manual process where, you know, then you have to like engineer some things to fix that and randomize that. So I think that's the issue, that we think of it as the simulator, and then we think of there's some stuff that the robot does in the world. But I think we kind of need to think of all of it as one and not really so much separate the simulation from the reality.
Dieter's turn.
Yeah, well, I think for the sake of this discussion, I think we can actually separate the simulation from the models and the real world as much as possible. So I still strongly believe that we need really accurate simulation models. We've seen with the kind of simulations we have right now, which are not quite at the level that we actually want, right? We've seen some success in robotics through techniques such as domain randomization. This came up several times here in the discussion. But again, I think the better the simulators are that we have, the better we know what to randomize over, and we make it so much easier for our robots then to be trained in these environments rather than crazy domain randomization. And I brought up this intuitive connection to imagine our babies would grow up in domain randomized worlds the way we're using domain randomization right now, and I'm pretty sure their brain would go crazy, right? I'm not sure that would grow to generate any useful behavior. I think we do all agree, of course, that we will always need some kind of handling of the discrepancy between simulation and the real world, because we will never get there perfectly. But I think we should really shoot for making that gap as small as possible, so that we know where the uncertainties are, and we can make these adaptations from the simulation to the real world as quickly as possible. Also because otherwise the behavior that the robot will exhibit in the real world might be dangerous, right? During the phase of when it has to be retrained. So I think we should really shoot for highly accurate simulations. And I think these are the key points.
Very much, Dieter. So Shuran, your closing statement.
Okay, so I think the high level idea that we want to get out out of this conversation or like discussion is I really want to highlight that we want to let the students or the community know that it is not only the accuracy of the simulator matters, but there are also a lot of other things that the community should actually care about. I think Deirdre actually just kind of summarize that. We need better domain randomization method, which is actually not directly related to the accuracy of the simulator. So I think as a community, we should focus not just on the improving the accuracy of the simulator, but also invest in effort on complementary methods on improving the diversities or better improving the diversities, or how to better model uncertainties or better understand what is easier to model, which part is harder to model, and how to improve like efficient real-world learning in order to compensate inaccurate simulator. Yeah, so that I think that's my like idea what I want to get out of this discussion. Yeah.
And so finally, Karen, your closing statement.
Sure. So there's really just two fundamental ways to solve the problem of Sim2Real to my mind. You either need to have a better simulator or you have a better controller. We've seen a lot of efforts put on, developing a better controller to solve Sim2Real, which give us some, anecdotal success, I would say. But we will have, but I still feel like we haven't arrived at this more principled task agnostic solution to Sim2Real problem. So I propose we start trying the other approach. Let's have a better simulator. And how do we achieve that? I don't know, but the two things that I can see, or I found that we as a community can really improve is the first one is how we leverage data to improve the simulation in a more effective way. There's definitely a spectrum of ways to use data to influence the outcome of simulation, from system identification all the way to this model-free RL, right? And people have invested a lot on those two ends of the spectrum. I feel like there's a lot of opportunity in the middle, to have a better, more principled way of using data for our simulator. And another thing I think that we as a community probably should be thinking about is to establish some kind of unified abstraction and hierarchical, for modeling, like structure for modeling, as well as some more composable physics engine. I don't even know what it's called yet, but I would just, the way I imagine this is kind of like a CAD tools, right? Like people have those kind of composable physical engine that can be composed to simulate multi-physical phenomena, through a common interface. And that would be something that I think worth investing, for this community. Yep, that's it.
Well, okay, so that concludes our debate. Very interesting points that were brought up. So I hope to see you all at the panel at the end of the workshop. And thank you very much for accepting the invitation for this debate.
Thanks for joining.
Thank you. Bye, everybody.
Nice to see everyone.
Yeah,
Bye.
thanks.
Bye. Bye.